Welcome back to the next lecture of high performance scientific computing. So now we will discuss as to why do we need to do parallel computing in the first place, and why can't we do simple serial computing like we have done in the past. To talk about this, let us now look at the contributions of these two gentlemen. Both of them are engineers from the 70s, Mr. Gordon Moore from Intel and Robert Dennard. And we will talk a little bit about what is called as a Moore's law, and then finally about Dennard scaling. So what Gordon Moore had predicted was the total number of transistors on integrated circuits would double in a per square area. So what Moore's law essentially says is the fact that the number of transistors that can be packed per square inch or per square mm doubles roughly every 18 months. So what impact does that have? The more number of transistors that are there, that means you can construct more logic circuits. That means you can construct more circuits like adders, multipliers, so on and so forth, which are essentially doing the calculations and the computations that you need, effectively doubling the power every 18 months. Now, you would wonder that is there an ultimate limit to Moore's law? And as you can see, right from the 1970s to about like 2018, Moore's law has been standing. The basic element of any computing device is the MOSFET, or the metal oxide silicon field effect transistor. This is the building block for making all the logic gates, and from the logic gates you have all the complicated circuits which do the computations for you. This essentially consists of a gate, a drain and a source, and if a voltage is applied at the gate, then there's flow of electricity from the source to the drain. This is obviously built on a silicon substrate. Now, when we talk about Moore's law, we essentially talk about the feature sizes of these MOSFETs, how big or how small they are. Now you can see the dramatic decrease in size of these gates. So few decades ago it was about 50 nanometers. This image is a slightly dated image. So you can see a 50 nanometer gate which is now going further down to 30 nanometers, 20 nanometers. In fact, today's modern computers are built on what is called as 3 nanometer technology. So the size of these gates has gone down almost to the size of 3 nanometers. This is incredibly small. Obviously, we cannot keep pushing the limits of this, right? Because finally we will reach atomistic scales. So what happens? Now, the other aspect of this is that when you're dropping the geometric size, or whether you're dropping the dimension by a factor of k, you have to drop the voltage by a factor of k, you have to drop the current by a factor of k, capacitance by a factor of k, the delay time, because it takes some time for these circuits to switch on and switch off, that delay time goes down by a factor of k, and the power dissipation, more importantly, goes by k square, because that's power is basically voltage into current. Now, while we still continuing to push the limits of Moore's law by packing more and more transistors, by reducing the feature size, as I said, so today's technology we are able to produce transistors at 3 nanometer sizes. Dennard scaling is already broken because we cannot continuously drop voltages, currents, so on and so forth as we drop the dimension. The reason is because to identify the binary states of 0 and 1, we need to have a certain finite voltage, and that voltage limit has essentially been hit. So what happens? So if you look at the last 35 years of microprocessor data, you can see the number of transistors that are being packed onto these integrated circuits is increasing dramatically. But what we really are interested is what is the serial performance or what is the single thread performance of operations. And we see that in the last decade or so, this has sort of asymptoted to a finite value. What is also asymptoted is the frequency at which these integrated circuits operate. Every integrated circuit has something called as a clock, which is basically a square wave pulse, which is used as a time counter to do these mathematical operations. Now, in the past, if you had, say, a 60 megahertz computer, you just had to wait for a few months, and then a few months later, there would be a 120 megahertz computer which would do computations roughly twice as fast as the previous computer, based on the same hardware. But over the last few years, you would have seen that the so-called clock speeds have sort of frozen to about 3 gigahertz on desktop machines and to about like 1.5 gigahertz or even lower on laptops and low power devices. It also means that the typical power consumption of these integrated circuits has reached an asymptotic limit. But what has changed to increase or boost the computational power is the increase in the number of computational cores, because our software programs are growing ever more hungry and it needs more and more computing power. So the number of cores are increasing. About 2 decades ago, if you were to go and buy a computer, the only option typically you would have is for what is called a single core machine. Then you have the concept of dual core, quad core, so much so that today you get machines or processors with excess of 128 processing cores on them. Even low power devices like cellular phones today feature multiple CPU cores. So the only way to increase your computing power is to increase the number of cores. What impact does this have for a regular day-to-day computer user, right? We are not talking about scientific computing at this moment, but let us say that you're a regular computer user. So one core might be handling the task of, a web browser. Another core might be handling the task of a spreadsheet. Another core might be handling the task of an editor. Another core might be doing something related to either video watching or something else. So typically in a user's computer, there are multiple processes which are running. Each of it is sort of assigned to a computing core. The assignments typically are then handled by the operating system, which schedules these operations on these different computing cores based on the priorities of the user. Now, the only way to increase the power or increase the computing capacity of these machines, now it's very clear, is only by increasing the number of computing cores. Now, what if you want to harness all this power for a single computation? So this is where parallel computing comes in. So let us say that I have a computer which has maybe 8 cores or maybe 128 cores. How do I exploit and run my scientific compute at the fastest possible speed? And that involves parallel programming. And because of the reasons mentioned before, you cannot run away from parallel programming, because in the future you're going to have only multi-core CPUs coming about. The main issue is that people do not think in parallel while programming. One solution would be to do some sort of automatic parallelization, like let the compiler writers figure out how to parallelize a code. You just write the code the way that you normally do, and the compiler will then figure out how to do the parallelization. But this has been sort of a disaster over the years, because unless you understand the algorithms and you understand how your code works and how you can exploit parallelization from your algorithm, it's very, very difficult to efficiently use all these parallel computing cores. I would like to narrate an anecdote at this point of time from the time when I was a graduate student about 20 years ago. At that time, these multi-core machines were just about coming out, and we were in the process of writing our own parallel algorithms and own parallel code. And I was given a suggestion that there was this new compiler which was able to do automatic parallelism. I was initially skeptical about it, but I was then convinced by my supervisor to use this. And when I tried using this automatic parallel computer, my computer code, instead of running twice as fast because it was a dual core machine, actually started running 50% slower. Because the code did not automatically understand, or rather the compiler did not automatically understand the algorithm that I was actually implementing. So it was in my hand to exploit the parallelism rather than on the compiler's hand. There are other limits and roadblocks to parallelism which are not so obvious. And one of the fundamental things that we need to do is that whenever we do parallel computing, we need to send messages or information between different parallel cores. And this is where Amdahl's law comes in. Now, let us take an abstract example of this. Let us say that our task is to compute the global sum of a set of integers or a bag of integers. And let us say that this bag of integers has 10,000 integers. And let us say that you are doing the compute using a human computer, a person like me, who is able to do one addition per second, something which is reasonable. So if I were to take this bag of 10,000 integers and start the compute, it would take me 10,000 seconds to get to the results. But now let us assume that you want to do this computation faster. And let us say you have 10 similar human beings, similar to the mathematical capability that I possess, in the room, and we want to now do this computation of this global set of integers. The naive assumption would be that since we have 10 human beings, we have 10,000 numbers, each person would take 1,000 numbers, and we would be able to compute the answer in about 1,000 seconds. But that's not correct, because there are certain other overheads which come in. First of all, there will be an overhead of distributing the 1,000 numbers per person from the bag. That takes some finite time. Then, once each person has computed their local sum, we need to get back their local sum and then do the computation of the last 10 digits. Even if we disregard the time it takes to give these 10 people the messages, like the 1,000 messages 1,000 numbers that each person needs to receive from the bag, and the one number that each person needs to send back as their local sum, let us disregard the cost of communication at this point of time. Even then, it's not going to take us 1,000 seconds, but it is going to take 1,010 seconds to make this calculation. Now, this has very interesting implications. Let us increase the number of people from 10 to 100. So how much time will it take now? So each person would receive 100 numbers. So each person would be able to compute their local sum in 100 seconds. But now I have 100 local sums, and that needs to be computed by one person. Again, we disregard the time it takes to communicate all these numbers between people, and only one person will compute the final global sum. So that will take another 100 seconds. So in all, it will take 200 seconds if I use 100 people. So in short, what I'm trying to tell you is that the time it takes, or the speed up that I get if I use 100 people, is that it takes 200 seconds compared to the 10,000 seconds if it would take if I had only one person do it. So if I put 100 times more resources, I actually go only 50 times faster. And this has very, very interesting implications. and it is formalized by what is called as the Amdahl's law. Amdahl's law states that if P is the proportion of a program that can be made parallel, remember that every task that you have can be broken down into two parts, the one which can be parallelized and one which necessarily cannot be parallelized. Going back to the example of the bag of integers, computing the local sum amongst n people is a task which can be parallelized. But computing the global sum, where we need to collect all the local sum and then compute the global sum, that is a task which has to remain serial and cannot be parallelized because only one person needs to do that. So let us assume that P is a proportion of a program that can be made parallel. And then obviously 1 minus P is a proportion that cannot be parallelized, has to essentially remain serial. The maximum speed up that can be achieved if you have n processors, in the bag of integers example, n processors were the 100 human beings that we used, is given by this formula where speed up, which is a function of n, is equal to 1 over 1 minus P, where P is a proportion of the program that can be parallelized, plus P by n. Let us assume that we have infinite processors, infinite number of processors. So the term P by n will now tend to 0. So the maximum speed up, theoretical maximum speed up for S, if it is n is infinite, is 1 over 1 minus P. And this has some very interesting results. So let us assume that the parallel portion of the program is 50%. So you have a code or you have an algorithm, 50% of the tasks are parallelizable, 50% of the tasks are not. So 1 over 1 by P, as n tends to infinity, turns out to be just 2. So that means even if I throw millions of processors at this problem, I can at the most go 2 times as fast. If the parallel portion of my code or my algorithm is 95% parallel and only 5% is serial, then the theoretical upper limit is just 20. I cannot go more than 20 times faster. This has serious significance. So a code which is 99% parallel can at the most go only about 100 times as fast, not more than that. And the reason why we say that this has serious implications is that today's modern desktop computers, they themselves have computing cores of the order of 64 or 128. Large high-performance computing parallel machines have computing cores of the order of millions. Now, if I'm not able to take more than about 1,000 processors and get any more speed up, then most of my parallel algorithms or large parallel machines are effectively rendered useless. And this is one of the basic problems or other basic mistakes that researchers and users of high-performance machines make when they start. They see that they have access to hundreds of processors and they immediately tend to use all the resources that are available to them. They will throw large number of processors at the problem only to realize the fact that they're not going to get any performance speed up. So one of the first things that one needs to do is figure out how much is the parallel portion of one's algorithm. The second thing obviously is to maximize the parallel portion of one's algorithm, and only then you'll be able to exploit the larger number of processors and get maximum amount of speed up.